Welcome, everyone. You know how you can look at a shape on a page and just wish you could turn it into a puzzle you could actually solve with numbers? Well, that's exactly what coordinate geometry is all about. We're going to see just how it works.
So here's the real challenge, right? How do you take something visual, something kind of abstract like a square or a triangle, and turn it into a hard math problem, something you can actually calculate and prove with zero doubt? And the answer? It's almost ridiculously simple, but this one idea totally changed the game for math. What do? We give every single point an address. That's it. This one little trick builds a massive bridge between the artsy, visual world of geometry and the super logical world of algebra.
Okay, so our first stop is the blueprint, the actual workbench where we're going to build and take apart all of our shapes, and that is the Cartesian plane. So what is it? Just think of it like a perfect grid. You've got two number lines, one going sideways, one going up and down, and they cross each other at a perfect right angle. And believe it or not, this simple setup is powerful enough to map out literally any flat shape you can think of. All right, let's get our bearings really quick. The line that runs left to right, that's your x-axis. The one that runs up and down is the y-axis. The spot where they cross, that's called the origin, or just point 0, 0. Every other point gets its own unique address, called coordinates, which looks like x, y. And hey, if you really want to sound like you know your stuff, the x value is the abscissa, and the y value is the ordinate. A little extra trivia for you. Now, these 4 quadrants you see here, they're not just there for decoration. They're actually like a built-in error checker for your brain. So let's say you do a bunch of math and you're expecting your answer to land in the upper left quadrant, but your final coordinates are both positive. Bam! You know instantly that something went wrong somewhere. It's a fantastic little diagnostic tool that's baked right into the system. Okay, our blueprint is all set up, so it's time to open up our toolkit and pull out the first tool. And I'm willing to bet this one's gonna look pretty familiar. We're about to build a kind of universal distance ruler, and we're gonna do it using something you probably learned a long time ago, the good old Pythagorean theorem. So what does this tool do? Its purpose is crystal clear. You feed it the addresses of any 2 points on the grid, and boom, it spits out the exact straight line distance between them. No physical ruler needed. So how do we actually build this thing? It's not magic, I promise. All you have to do is take your 2 points, draw a couple of lines to form a right-angle triangle with them. The length of the bottom of that triangle, that's just how far apart the x-coordinates are. The height, that's just how far apart the y-coordinates are. And just like that, you have a squared plus b squared equals c squared. See? It's really just Pythagoras wearing a clever disguise. And when you just rearrange that Pythagorean theorem a little bit, voila! You get this elegant formula right here. This is our shiny new distance ruler. It's ready to go. It can measure any line, anywhere on the plane. All you have to do is plug in the numbers. So let's put this tool into action. Imagine you have 4 points, and you need to prove, really prove, that they form a square. Now, your first instinct might be to just measure the 4 sides, right? But hang on, be careful. If you only do that, all you've proven is that it's a rhombus. To be absolutely sure it's a square, you need the full 6-point check. You use our distance ruler to measure all 4 sides, and then you use it again to measure the 2 diagonals. If those 4 sides are equal, and those 2 diagonals are equal to each other, then you've got yourself a square. No doubt about it. All right, tool number 2. This one's for the real precision work. We're going to call it our proportional divider. Think of it like a precision slicer for lines, designed to find the exact address of a point that cuts a line into any ratio you want. So just picture a line segment connecting 2 points. This formula lets you find the exact coordinates of the point that cuts it, say, 1/3 of the way from the start. That means the ratio would be 1 part to 2 parts, or m to n. It's incredibly, incredibly precise. And here it is. I know, it looks a little intimidating at first glance, but just take a breath and look at the pattern. All it's really doing is taking a weighted average of the x's and a weighted average of the y's, all based on that m to n ratio you want. Okay, now for the cool part. Watch what happens when you just want to find the dead center of a line. The exact midpoint. Well, the ratio for that is just 1 to 1, right? So if we plug in m equals 1 and n equals 1 into our big scary formula, look what happens. It simplifies beautifully. And this is where you get that aha moment.
The midpoint formula isn't some brand new tool you have to memorize from scratch. Nope, it's just a special case, a shortcut of the section formula. It all just boils down to a simple average. Average the x's, average the y's. Done. Okay, we've measured lines, we've sliced them up. Now it's time to bring out the heavy machinery. Let's get into the advanced tools, the ones that let us analyze whole shapes at once. We're going to focus on triangles here.
We've got two real power tools for this. First, the area formula. You feed it the coordinates of the three corners, and it tells you the exact area inside. And see those absolute value bars? That's just to make sure the answer is always positive, because, you can't have negative space. Then we have the centroid formula. This one's super cool. It finds the triangle's perfect balancing point, its center of gravity. And all it does is average the three x's and the three y's.
But that area formula has another really clever trick up its sleeve. It's the ultimate test for seeing if 3 points are collinear, which is just a fancy way of saying they all lie on the exact same straight line. Just think about it for a sec. What would a triangle made from 3 points in a perfectly straight line look like? It would be totally flat, right? It would have an area of 0. So if you plug 3 points into the area formula and the answer is 0, you've just proven they're all on the same line.
And this is where you can really see how our whole toolkit works together. The centroid isn't just some random formula you have to memorize. You can actually build it with the tools we already have. Watch. Step 1. Grab the midpoint formula to find the middle of one side of the triangle. Step 2. That line you can now draw from the opposite corner to that midpoint is called a median. Now, step 3, grab our section formula and find the point on that median that divides it in a 2-to-1 ratio. And guess what? That point is the centroid. It's amazing. Our tools literally build on top of each other. So there you have it. You've got a complete, really powerful toolkit now. The only thing left is knowing which tool to reach for to solve which kind of problem. So let's put together a quick little strategy guide. Think of this as your go-to cheat sheet. If your goal is to prove what kind of shape you're looking at, you grab the distance ruler. And remember that 6-point check for a square? If you need to find a point that divides a line, you're going to want the proportional divider, the section formula. And finally, if you need to prove without a doubt that a few points are all on the same line, you pull out the shape analyzer. That's the area formula. And you check if the answer is 0. Let's just take a second to appreciate the number 0 here. In coordinate geometry, 0 isn't just nothing. It's everything. It's the origin, the absolute center of our universe. And, as we just saw, it's the magic number that proves points are perfectly aligned. It's a surprisingly powerful and important part of this whole toolkit. So that's the power of this system. It lets you translate the visual, sometimes messy world of shapes into the clean, logical world of numbers and proofs. The entire toolkit is now yours. So the only real question left is, what geometric puzzle are you going to solve first?